Hello, everyone. I'm very excited to introduce Anna. She's a very experienced data analyst and have a lot of experience in payments industry. So thank you, Anna. Let's start.
Thanks. Thanks for the introduction. So my name is Anna Chaloska, and today I would like to talk to you about different ways to do feature encoding. So first of all, a little bit about me. So I'm Anna. I work as a data scientist in a payments company called Molly. Molly is a Dutch company based in Amsterdam, and it's a payment service provider, meaning that we offer a payment platform through which web shops are able to process their payments. As a data scientist, I work in the customer monitoring team, which means that my work revolves around building models for automation and optimizing of processes that are in the monitoring domain. So what I'm going to talk about today is categorical data. And shortly, what is categorical data? There are many different data types, right? But categorical data is anything that you can think of in terms of groups. For example, names, places, gender, job titles. All of these are types of categorical data. And what we see in everyday life, especially in the data science world, is that we see this kind of data as a good source of information for building models. However, with some exceptions, most of the models can't accept categorical data as such. The categorical data needs to be transformed in a certain way for the models to be able to understand it. And that is, it has to be transformed into numerical type. Now, the process of transforming this categorical data into numerical data is called feature encoding, and that's what I'm talking about today. A little bit about the data that I see in my daily life. So, like I said, I work in payments. What that means for the data is that the basic data type is payments. Now, payments, when you hear payments, it might sound immediately that it's mostly numerical data. And for sure, volume, which is a very important characteristic of a payment, is numerical. But there are actually many more data points around the payment that are from the categorical type. Think of payment methods, something like credit card, Ideal, Klarna. These are all categorical values. Or the status of payment, whether it's paid, canceled, and so on. The IP address, this is a tricky one. It looks like numbers, but it's actually a category behind it. The numbers don't convey a meaning. Country, where the payment is processed, and actually many others. So as we see, there are many types of categorical data that are revolving in the payment industry, and so I believe in many other industries. And this is actually the motivation behind my talk. I work with this kind of data, and I explore different ways of feature encoding. And my learnings I would like to share with you today. So what was my challenge? I was working on a regulatory model, and I had to use country as a data point. So these country names, they look something like this. So we see there are 195 countries, all the countries in the world, and they're not very straightforward to transform into numericals. I'll show later why, and I'll show later also how I fixed it. Before we go on into that, let's see how many of the people here ever use categorical data during model development. Let's show by a raise of hands. Okay, yeah, that's quite a bit. And how many of you then ever experienced a challenge into encoding it into numerical? Right, okay, well, I'm happy to see that, because then I hope the content of this talk will help resolve at least some of these challenges. So now I would like you to think of this challenge that you faced in your daily work. So when you face the challenge of encoding a categorical variable, and I would like you to keep it in your mind during this presentation, because what I'll do is I'll present different ways of encoding, and hopefully some of these ways could be applicable to your case. Then when you go back to work on Monday, you could maybe think about applying it to your use case and seeing whether your model performs better with this new way of encoding the data. So if you don't have such an example, it's also fine to use my example, but if you have something applicable to you, it could be also nice and more applicable. So what's the plan for today? Shortly, I'm going to show 3 groups of encoders, starting from simpler ones all the way to more advanced. For each of them, I will show when it's good to use them, when it is not good to use them, and also if you decide to use them, what to pay attention to. In the end, I'll provide a QR code with a summary of everything that I say, so that will include all the definitions, all the theory, also the examples, so you'll be able to scan it and take it home with you. And bonus there is there will be content on the Python built-in methods where you can find all of these encoders that I'll present about today. So everything I show today is easily integratable with scikit-learn pipelines, and it's based actually on a couple of libraries that you can find in the summary as well. So the goal for today, simply, we will learn about different encoding methods, and by the end of the presentation, I hope you will learn new ways, and you will learn how to choose exactly the one that you need that will help your models perform better. So the built-in methods I was mentioning, so everything that I showed today will be at least at one or sometimes in two of these libraries, scikit-learn, feature engine, and category encoders. Most of the time it's a single line of code that you need to add to your script, and it is easily integratable with the rest of the pipeline, which is pretty nice. So it's mostly about integrating it is not so hard as choosing what exactly you want to use, and that's what we're focusing on today. So then let's start. The first part, basic encoders, also more commonly known. Let's start with something called ordinal encoder. So this is a simple one. It just maps every category to a distinct numerical value. As the name suggests, it's good to use with ordinal data. And ordinal data is everything that if you put the values in order, it makes sense. It tells a story. Let's see an example. If we have educational levels, bachelor, master's, and PhD, this order makes sense. It tells something about the data that you're dealing with. So what we would do here with the ordinal encoder is we map each value to one numerical value, and then we replace the data accordingly. As simple as that. You can use this also if you're dealing with maybe customer ratings, subscription types, basic, advanced, premium, these kind of things. So there are all data points that have an order. But when it's not good to use it, when data is not ordinal, let's take an example of eye color. So we have 4 different eye colors. And if we encode them with the ordinal encoder, what we end up with is something like this, which is, the model will accept it and will work with it, but it will also think that blue is twice as much of brown of something, which, in reality doesn't really tell any context. So in this case, when we are not dealing with ordinal data, better to go with another approach, one of the ones that we see later. Second encoder is frequency encoder. It's actually similar to the label encoder, but here instead of mapping to a numerical value, we map to a specific count that we see of that value in the training set. It's nice when you have high cardinality because this decreases the cardinality of your data and makes it simpler for the model to find patterns, and it conveys some information about your data point as well. So for example, in terms of, if we have a data set with sold products, here we have chair, table, and plate as an example. Chair we see 3 times, table we see 2 times, plate we see 1 time. So when we replace it in the data, it looks like this. Say we're working on a net revenue model. The model will know that chair is the most popular sold product, table is second, plate is third. And in reality, we'd have many more products, like I said, with high cardinality, so this can be quite useful. However, there is a downside to this, is if all of or most of your values end up in equal number of observations, something like this. If we have 3 chairs and 3 tables, we encode the data, it would look like this. So if we see, it's any variable with a single unique value means nothing to a model. It won't be informative. So chances are later on in some feature encoding, in some feature selection step, this will be dropped anyways. So you might as well save yourself the work around this and go with a different encoder instead if you notice this kind of behavior in your data. Last one of the simple encoders, well-known One Hot Encoder. So here we create binary features per category. Nice to use when you have low cardinality, because then we make sure that the data doesn't become too big and sparse. Eye color is a perfect example for this. We have 4 different colors. We encode them. So basically, every column here shows where the row belongs. Like the first row has a 1 in the column called brown, which means that this person has brown eyes, and so on. So this is quite handy and can be understood well by the model. What you can do here is nice, skip the last column, you avoid multicollinearity, especially a problem in linear models. And why you can do this is because then we don't have black anymore as a column, sure, but black is still encoded. It's encoded with 3 zeros. And if you read this, it just means that it's not brown, it's not blue, and it's not green. So it must be black, right? Because there are only so many eye colors. Where you have to be careful is if you're working with products, for example, here. Product there can be different, right? So if we decide to drop plate as a column, that's fine. But if new products come along, like desk, they will have the same encoding as the one that we dropped. And same encoding means information loss. And now, it doesn't mean that you can never use this, but it means that it's good to check with the business whether this is an information loss that is not, that would make the model not applicable anymore. So this is something to pay attention to, and if it's a problem, then it's better to go with all of the columns. So one more thing, when it's not good to use it with high cardinality, so the opposite case is if we have, for example, day of the year. There are 365 days of the year, and if we create a binary column for each of them, we end up with something like this, which, yeah, is very big and sparse data, and will probably just confuse any model that we ingest this into. So for this kind of data, we'll see other techniques later that it's better, that would be more applicable. So that concludes the first part, the simple encoders. And we move on to the next part, which are also relatively simple, but they're powerful, because especially because they can be used as helper encoders to other encoders. So you can use this in combination with others, with ones already presented and some others from late. So let's see. First one is called rare label encoder. And what it does is it groups infrequent categories into one rare category. It works well when you have cardinality, and because it decreases the cardinality. And another reason is here high cardinality should be accompanied by underrepresented categories. Let's see how that looks in an example. If we have data about payment methods, so here we have values like ideal, Klarna, credit card, right? And they appear quite a bit in the data set. We can see it in multiple rows. But then we see EPS, so forth, Belfius, and they are only represented by a single row. And this is not enough data for a model to be able to learn from, to find patterns. Probably it will overgeneralize on this, actually become overly specific on these categories, and will overfit on them. So what is better to do here is we apply the rare label encoder, which means that all of these values that are underrepresented will just end up belonging to a single rare label class. And this rare label class will, if you read it, it will mean something like, yeah, we have ideal, Klarna, credit card, and then all others. This is very nice to use, but important to note here, like I said, it's a helper encoder, so you still have to apply another encoder next to it, because here we still don't have numerical data. So after this, you can choose another method that is in accordance with the definitions, and continue encoding. Be careful to not use the rare label encoder, even if you have underrepresented values, if those rare values are meaningful. So let's see an example. Let's skip to the same example, right? So with the payment methods, let's say we encoded this with rare label, it's fine. And then in production, we see something like Apple Pay, right? So this is something that we've never seen on training data before. And the rare label encoder, what it will do, it will just automatically bucket it as a rare label, because if it's only seen one of them. What's the problem here is that maybe this is a new product, and by bucketing it with all the products that didn't perform so well in the past, maybe we're not giving it a chance in our predictions. So this is another scenario where it's good to check with the business and the stakeholders that this is not leading to too much information loss, and we're not blindly allocating to the rare class. Hash encoder. Hash encoder is about applying a hash function to create hash buckets. So again, we're bucketing it, but in a different way. Why it's different, we'll see now. So first of all, when it's good to use is when we have very high cardinality. Hash encoder is quite nice. When you have to be memory efficient. And when we want to reduce the dimensionality of the data. A good example for this is author names. because this feature by itself is something that initially contains a lot of authors. There are a lot of authors in the world, and chances are when you go to production, you will have many more as well. So what the hash encoder does is you choose a hash function, and then you apply it to each of them, and they get encoded into single buckets. So in this case, Jane Austen and Mark Twain ended up in bucket number 0, J.K. Rowling and Agatha Christie in bucket number 1, and George Orwell in bucket number 2. To be a bit more specific about how this works is that we apply a hash function, and then in order to make sure that we have as many categories as we expect, we apply a modulus on top. So for example, a mod of 3 in this case, it will always give a remainder of 0, 1, or 2, and that's why you end up with 3 groups. So it's important to apply that last step in the hash function. So when you specify how many buckets you want to see, that's the mod that will be applied to the hash function, and that's how then it's decided which bucket each of the values will belong to. Now this one, why it's nice is, first of all, it reduces dimensionality, but also it can work on the fly. You don't have to store anything in memory. You don't have to store this mapping, because the hash function can be just applied on new values. And the third reason why it's nice is because when you have new unseen values in your data in production, let's say someone new in the world wrote a book, you can directly hash it and allocate it to a bucket without having to go back to your preprocessing and encoding again. So this makes it different from the previous encoders. So yeah, that's how our data looks like. From 5 different values here, we ended up with 3, but in reality, this would be like from thousands and thousands to a smaller number. It's not nice to use it on ordinal data, because then, if we apply it on, let's say we have this example with subscriptions, we can apply it. But in this case, if you see basic and premium end up in the same bucket, and this leads to some important information loss, because here we have meaningful information in the ordering of our variables. So here the label encoder would make more sense. So the order relationship between the subscriptions, we lose it here. So that's why we don't want to do it. So that concludes part 2. And I'm moving on to the last part. It's about the advanced encoders. And what makes them different from everything that we saw before is that these encoders don't only take into account the feature itself, they also take into account the target. So they pull information from the target variable as well to make something meaningful for the model to learn from. And let's see how that's possible. The first one is the mean or target encoder. And the name comes from the definition that for each class of a categorical variable, we calculate the mean of the target for that class. It's nice with high cardinality again, and nice to use when you have regression or binary classification. With multi-classification, there is something we have to be careful with. I'll show that in a bit as well. Let's first see the binary classification, have the payment methods here, and whether the payment was fraudulent or not. So let's imagine this is a payments data set where we see whether a payment was fraud or not, and we see its payment method. So for ideal, how would we encode it? So we take the class ideal, and then we calculate the mean of the values under the target. So here we have 1 0 and another 0, so the mean of 2 zeros is just a 0. So we'll encode ideal with a 0. Then we have Klarna, which has 1 and a 0. Their average is 0.5, so that will be our encoding. Similarly, for credit card, we end up with 0.66. And that's how we turn our data into something meaningful that basically tells how often in the past this payment method has been associated with fraud. And then when you have an incoming payment in production, the model knows that, okay, maybe credit card is actually the most susceptible to fraud. We should be more careful with creating a prediction. Something to be careful here, and it could be argued that this leads to some sort of data leakage. Why? Because basically here, we are taking into, when we're calculating the value for a single payment, we also take into account the target value of that single payment. And in production, when we have an incoming payment, we don't yet know its target. So it doesn't fully mimic how it would look in production. And the way to solve that is by something called leave one out approach. So basically, if we say, let's say that for the first row of credit card, we will encode it by only taking into account the second and the third one. And then instead of 0.66, we end up with a value 0.5. So this is an approach. If we want to be extra secure, there is no data leakage. Another thing to be careful, what I mentioned earlier with multi-class classification is if we have more than two features more than two classes in the target. Here we have status of payment, paid, cancel, and declined, and let's say we want to predict it. What we see here is the target is categorical, and we can take a mean in categorical data. So what we can do instead is we can first apply one hot encoding that we covered earlier. Now we apply it on the target, and then for each of the resulting columns, we can apply the target. Encoder on top of them, and that way we will encode. Encode for each of the different values in the target variable, and we avoid the challenge of multi-classification. When not to use it is when we have dependencies between categorical features or the feature-target relationship changes over time. So for example, in this case, we see that credit card and country A always led to fraud, and credit card and country B always led to non-fraud, let's say in simple terms. Now, if we applied the target encoder as we did before, our data would look something like this, right? We had 0.66 before. But still, 0.66 and A leads to fraud, 0.66 and B leads to non-fraud. So we actually then expect the model to figure out this combination and learn it to tune it, to find the parameters. But we have an expectation of the models to figure this out, although we already found this relationship between payment method and country as features. And in this case, what could be nice is take one step back into feature engineering and think about how we can create one feature that could combine payment method and country together, because we know they are related. And this could be as simple as concatenating the two, for example. And then, only then, we apply the target encoding on top. So that could be the workaround. The next one I'll cover is the weight of evidence encoder. So this one is similar to target encoding, takes information from the target, but only with a different formula. Instead of the mean, it looks the ratio between goods and bads. What goods and bads means here is goods is everything that has a target of 0, bad is everything that has a target of 1. The reason for it is that, because this comes from, this encoder originates in banking, and there was always the need to see if someone is a bad client or is going to be going into default. So here we're looking at the ratio between the good and the bad class and taking the log. In other words, this is logots, more commonly known. It's nice to apply it to nominal data, so not ordinal, and nice to use in logistic regression models because of that logots component. So for example, in this case, we look at the ratio between, so probability of 0 here is, we have 3 out of 4 zeros, so it's 0.75. Of 1 is 1 out of 4 is the 1, so it's 0.25. And the ratio, we find the log, and it's 0.47. Similarly, we find it for credit card. Now, something nice to notice here is that, the log of positive that ends up, when the log is positive, it indicates to the model that there were more goods than bads, and the absolute value indicates how much more, and similarly with negative. So that's how it conveys the information to the model. And then we can easily apply it to logistic regression because that it also works with logots. Not nice to use with ordinal data because then we're losing quite a bit of meaningful interval information. Finally, the last one is the cat boost encoder. Simple way to put it is a time-aware target encoding. Basically works the same way as target encoding, but instead of taking into account all of the data, it only takes into account the rows that happened before a specific row. So it's nice to use it when there is a time dependency, and there is a feature-target relationship that changes over time, which, if you remember, was a downside of target encoder. If we see the example, here let's say that we want to calculate for credit card the last row. We will take into account the two ones that happened before, We'll calculate the mean of those, and we'll apply it to the last one. So something important to mention here is that for every row, we will have a different value. So for every different value of every different category, we'll have a different value, which makes this encoder more computationally expensive. So before using it, make sure that it's feasible in your setup. When it's not nice to use it when you have limited data, or very large feature sets because of computation. So for example, here we have too little information on these medical symptoms, leg and arm pain. It's insufficient data, so it's better to apply something like rare label encoder first, and then continue with CatBoost. So that concludes all the encoders. And before I close the talk, I will quickly show you how I solved my challenge. That was about representing countries' data in the regulatory model. So basically, the challenge looked like this. I had this countries' data table, and feature, and then I had to build a regulatory model which, because of some limitations, had to be logistic regression. Something had to happen in between, and the first approach was, okay, let's One Hot Encode, but that ended up like this, and that wasn't very useful for the logistic regression, so instead went a step back and looked at the countries. What's nice is that there can't be more countries, well, most of the time appearing in the world, so we don't have to worry about new values coming in production. We noticed some values being underrepresented, so we first applied rare label encoder. And because of the logistic regression requirement, what was most applicable here was the weight of evidence encoder. One last remark I will make is that always fit transform on train set and transform on test on end production. So that will make sure that you don't introduce data leakage in your data, in your model. So that would look like that. So that concludes my talk. Here's the QR code that I promised in the start. You can scan it, and you will end up with a summary of everything that I said, when to use the encoders, when not to use them, what to pay attention to, their definitions, also including the examples that I gave, and on top also the built-in methods where you can find them in Python. Now you can think back about the examples that you thought about in the start, and hopefully something of this was applicable to your case, and when you go back to work on Monday, you can try it on your model, and hopefully it helps it predict better. In my case, it helped performance quite well. Thanks a lot, everyone, and I'm open to questions. Also, after this talk, you can approach me.